Hello everyone, I welcome you to this NPTEL online course. So during the course, I'm going to discuss the chemical process involved which are at the cornerstone of environmental engineering now. Anyway, before I go further, I would like to express my thanks and gratitude to Dr. Bill Batchelor, my advisor, from whom I learned most of my technical knowledge, I guess, right? So let's move on. And I guess you are concerned about, is this relevant to you? So anyway, this course is designed for master's students and environmental engineering professionals or consultants. So this course will give you a basic idea, I guess, the fundamentals of the chemical process involved in environmental engineering. So the expectations from this course, once you are done with this course, you should be able to critically analyze and, if required, quantify the chemical changes within either an engineered systems as in STPs or CETPs, or look at and analyze critically again any of the natural systems that you would come across. Okay? So again, relevance, how is this relevant to you now? I'll give you two examples, let's say. So the first aspect is to give you a background about environmental engineering now. Any aspect of environmental engineering, when you look at it, there are going to be three aspects now. So here we have the physical, chemical, and biological process involved. So these three are more or less the cornerstones of environmental engineering, the fundamentals per se. So in this particular course, we are going to talk about the chemical process involved within environmental engineering. Again, it's not chemistry now, so those people who have an apathy towards chemistry, don't be thrown off right? Because these are the chemical process, so we won't be going into great detail with respect to chemistry, maybe a little of it, but mostly we are going to discuss the chemical process now. So regarding the example to see, I guess, or to let you know how it's relevant to you. I'm going to look at one example that I came across recently that I think is pertinent here, right? So we are going to talk about engineered systems, an example here. So people might have heard about the National Green Tribunal, the NGT, right? So it asked IIT Roorkee, or let's say me, its representative, to inspect some CETPs recently. CETP is a common effluent treatment plant, pardon me. So CETP is a common effluent treatment plant that caters to the industrial waste. So let's say there are 100 or 200 industrial houses there, and they discharge their waste to these CETPs, which then try to degrade the waste to the relevant standards, right? So obviously, let's just look at a summary of the process. So the influent here, and then primary treatment, right, coagulation, flocculation, and so on, which you are all well versed with, and I believe then secondary treatment, I think it's either SBR or ASP based, and then tertiary treatment, and then the discharge, right? So when we analyze this particular CETP, I took the samples from each unit stage and looked at it. I found that the COD was increasing, right, and the TDS too was increasing, and thus I guess is obviously an anomaly. You want to design your CETP to be able to reduce the BOD, COD, and TDS, and so on. So let's look at a pertinent or relevant example here to show you why, let's say, you need a background in the chemical process to be able to, have a career in environmental engineering now. So what they were up to was, they were dumping ferrous sulfate, right, a source of Fe2 plus, as their coagulant now, right? Again, coagulation and flocculation, as you are aware of, there are two major aspects involved. One, what is that now? Sweep coagulation. And the other aspect would be by charge neutralization. So again, coagulation, two major aspects, sweep coagulation and charge neutralization. So let's say traditionally people use alum, a source of Al3 plus, or you use ferric chloride, a source of Fe3 plus. So how they traditionally work is, they form complexes. Let's say if we are taking the case of Fe3 plus, they can form, ferric hydroxide complexes now, right? And the charge too, obviously, I guess, let's say, Fe, OH, let's say I say thrice, this is one ferric hydroxide complex. This obviously would not help with charge neutralization, but would help or assist with sweep coagulation. So charge neutralization, what do we have here? We have the colloids which are relatively negatively charged, and you have your coagulant which is relatively positively charged, or these coagulants as in Fe3 plus form aqueous complexes which again have, depending upon the hydroxide concentration there, right, you are going to again have a positive charge. So they are going to be able to neutralize the charge of the colloids, letting them aggregate, right. And then the other aspect is sweep coagulation, wherein the ferric hydroxide, the solid, can precipitate out, especially if you dump considerable amounts of, not dump, pardon me, add ferric in relatively higher concentrations now. Yes. So but what's happening with Fe2 plus, and why is it a very poor substitute for Fe3 plus now? So Fe2 plus, right, it forms little to no aqueous complexes. So here for charge neutralization you need to look at complexes. So at most pH, right, ferrous, pardon me, does not form complexes. So your charge neutralization can be affected there, and more specifically you will not have sweep coagulation because Fe2 plus does not form a precipitate, let's say, or does not precipitate out at most pH and most doses. So you need relatively high pH, and you need to have very high pH, right, and very high doses of Fe2 plus to be able to get your to have an efficient coagulation and flocculation mechanism. But why is the industry using that? Because source of Fe2 plus is cheaper than Fe3 plus and Al3 plus. But what's happening now? So you are unable to have an efficient coagulation and flocculation process, and that's leading to an increase in TDS. Yes. And also what's happening is, as you know, Fe2 plus, right, can be oxidized by oxygen to Fe3 plus now. So what does this mean? Fe2 plus has an oxygen demand, right. So again I believe this is the reason why I see that the chemical oxygen demand is increasing. So to be able to quantify that, let's say, or to at least be able to calculate the pH at which your system is going to be relatively more effective, let's say, you are going to look at the equilibrium related aspects. So let's say at the end of this course, at the fag end of this course, you will be able to critically analyze and then understand, and obviously again quantify as in put a number down. You know, most people will have a generic idea, but you as a professional should be able to quantify the relevant aspects. So that's what you will be able to do at the end of this course now. Okay. So we'll move on. So I guess we'll look at a brief course outline. A detailed course outline which will give you an idea about what to expect from this course will be available on the website. So course outline, so first we are going to have an introductory class which is going to be this session, and then next we are going to talk about the fundamental chemical process which are equilibrium, right, and then we are going to talk about the relevant aspects with respect to equilibrium, as in those aspects which not define I guess, would drive equilibrium, let's say, right. That's usually going to be the Gibbs free energy now, and we are going to look at the various models. And then the second major aspect would be, other than equilibrium, it's going to be kinetics now. Yes, again reactions, relevant reactors as in a plug flow reactor and CSTR and so on. So let's say we'll have one more look at these reactors. Let's say, for example, I want to model this room. Let's say, assume for my sake, and please excuse my poor drawing skills I guess, right, I have a contaminant that's flowing through the door of this room, and again there's an exit to this room. Let's say there's a window, let's say. Now I want to, and there are reactions occurring, right, and I want to model the concentration of this compound in this room with time. So I'll need to be able to come up with a case of ideal reactor here, and here let's say if the fans are turned on, I can say that this is a CSTR, a continuously stirred tank reactor. I think people use completely mixed flow reactor too. And once I define that system, I'll be able to develop a model and then able to predict or model the concentration of the compound in the room with respect to time, right. Okay, again moving on. So again we are going to have equilibrium and kinetics, and then we are going to discuss the four major aspects in environmental engineering, or the four major sets of chemical reactions. So the first one would be acid and base reactions, and then we are going to again discuss equilibrium and kinetics again in context of acid and base, and then moving on aqueous complexes, Again, we are going to discuss equilibrium and kinetic related aspects in complexes. Again, precipitation and dissolution, again equilibrium and kinetics, relevant aspects there. And most importantly, oxidation and reduction or the redox reactions and equilibrium and kinetics here. So obviously kinetics would have a lesser role to play in the acid-base reactions and aqueous complex. Kinetics has a lesser role to play. Mostly they are defined by equilibrium. But precipitation and dissolution, usually you look at kinetics, and also for redox you look at kinetics again. So we are going to be able to go through the major aspects here. So first we'll look at equilibrium and kinetics, and then the four major sets of reactions or types of reactions which we usually encounter in environmental engineering, and then look at the relevant aspects again. So if we are going to look at the schedule, right, so we see that we have a couple of weeks for equilibrium, and then again a couple of weeks for kinetics, where we are going to discuss the fundamentals now, right, and then we are going to look at the applications of equilibrium and kinetics in acid base, spend relatively less time on aqueous complexes and precipitation and dissolution, and then considerable time on redox reactions because they are ever present and are of great relevance to environmental engineering per se, and then some time on your environmental organic chemistry now. Again, obviously if you are dealing with microbes, and because most of the nature also we have organic compounds, we are going to have a brief look at that, right? So moving on, I guess you want to know, let's say, some of the aspects or textbooks that you need to refer to. So in general, a very good book, to refer to is Water Chemistry by Mark M. Benjamin. And I'm not sure if it's available online. So I'm going to suggest you another book that's available online through most of our libraries, and that's Water Chemistry by Brezonic and Arnold, right? So preferably look at Water Chemistry by Mark M. Benjamin, and if that's not available, you can look at Water Chemistry by Brezonic and Arnold. And in general, let's say there are some concepts that you want to dig into, right? You want to develop a much more fundamental understanding of the concepts. So then you can refer to the Holy Bible or the Holy Grail here, let's say, Aquatic Chemistry by Stum and Morgan. And this is the Holy Bible with respect to the chemical process involved in environmental engineering now. Okay, moving on. So let's say we are going to discuss the fundamentals of chemical process here, right? And I believe I have an example here that will illustrate to you why we need to look at equilibrium and kinetics. But I believe here we are going to first have some terminology. So we talked about chemical process now, right? And what is that now? What's a chemical process? What do you understand by that? Anyway, I'm not one for mugging up, definitions and such. As long as you are able to develop an understanding of what it is that we are looking at, that's good enough for me. Anyhow, so chemical process, I guess, occurs when a material undergoes a change in the chemical bonds, right? It occurs, again I repeat, a chemical process occurs when a material goes or undergoes a change in the chemical bonds now, or you can call that a chemical reaction too. Let's have that in our background for now. And then moving on, I want to illustrate an example. So here we have TNT, trinitrotoluene. I guess that's an explosive. Yes, you are aware of that. So here we have the relevant reaction for combustion. Yes, combustion of TNT, the solid form, going into, I guess, gas and solid and soot, I guess. And here we have the change in enthalpy during combustion of the solid. And obviously you see there is considerable energy released. Negative more or less means that it's an exothermic reaction, and you are having considerable energy release. And keep in mind that these are at the standard conditions though. Yes. And the next example we are going to look at is oxidation of glucose, right? And thus glucose, think of having a chocolate now, I guess maybe sucrose. Anyway, glucose, I guess, it can be oxidized by oxygen, as you are aware of. For example, if I let glucose stay open to the atmosphere, this is a reaction that I can expect, right? And again, look at the change in enthalpy now, right? It's minus 2800. It's almost or near the change in enthalpy that you would observe during the combustion of TNT now. Okay, think of this though. If I smuggle TNT in here and throw that out here in this room, the people who are sitting here, they are going to scatter out. But let's say if I bring glucose here and spread that out in the atmosphere, no one's going to run. They're only going to look at me as if I was a madman. So please take a couple of seconds and think of what's the aspect here that we are missing now. Both more or less release considerable amounts of heat energy, right? So what are we missing here? So obviously the aspect is that you want to look at how fast are these reactions going through, right? And in that case we come across kinetics. How fast are the relevant reactions now, right? For example, TNT, there are combustion of TNT, it's a remarkably fast process, or the kinetics is very fast. So that's why you would see considerable energy released within a short span of time. But oxidation of glucose though, the kinetics is relatively slow, or remarkably slow, pardon me. Yes, and that's why even though the energy released is comparable to the energy released during TNT combustion, right, you have the energy release over a considerable period of time. Yes, so here we are concerned about equilibrium, as in what happens after the system has reached the maximum extent possible. So I guess I use this example to illustrate that we always, whenever we consider any system, we need to look at, are we dealing with kinetics or are we dealing with equilibrium? So let's move on, I guess. So again, the fundamental aspects of chemical process, we are going to talk about equilibrium and kinetics. So equilibrium will give us an idea about how far can the system go to, how far can this chemical process go to, right? And keep in mind that it's a state. Equilibrium is a state of the system. And please pardon me for my poor handwriting skills, I guess. So equilibrium defines a state now. And people talk about, when people talk about equilibrium, they say, you know, forward reaction, rate of the forward reaction is equal to the rate of backward reaction and such. But I would like to think of that as they are the symptoms, let's say. But what is equilibrium now? It is the state, let's say, which you would describe when a chemical process has gone to the maximum extent possible under the given conditions of temperature and pressure. Again, I repeat. So equilibrium is a state when a chemical process has gone to the maximum extent possible under the given conditions of temperature and pressure. Please keep that in mind. The temperature and pressure are an important aspect here. Again, layman's knowledge. So equilibrium tells us about how far does the system or can the system go to. And the next aspect obviously is kinetics. And what does that tell us? That gives us information about how fast is the system now. Again, layman's terms, but I think I'm trying to help in your understanding rather than mugging up definitions now. And kinetics, what is that? It's not a state obviously, it's a characteristic. It's a characteristic of the system that tells you how fast or the rate of change of your chemical process, right? So again, equilibrium tells us how far can the system go to, and kinetics will tell you about how fast can the system go. And let's see what I have next. So I guess in general, when we look at any system, we will need to be able to analyze, okay, what aspect do I need to consider? Do I need to consider the equilibrium related aspects or the kinetic related aspects? So in general, we break them down into equilibrium control, kinetic control and mixed control. So let's see what they are about, let's say. So for example, let's say, you know, I'm looking at, let's say, acid and base reactions. Okay, acid and base reactions. And let's take two examples here. One is I'm adding drops of acid in a beaker that is continuously stirred, and this is my symbol for mixing, I guess. And then I measure the pH after a few seconds, let's say, after 2-3 seconds, let's say, right? And the other case is, let's say you have a, let's say a water droplet, you know, during rainfall, I guess, that's coming down, right? And you have carbon dioxide in the atmosphere, let's say, and then you are going to have the relevant acid-base reactions, yes. And the pH of this particular water droplet will obviously decrease now, right? So if you look at these two systems now, you know, we need to be able to, let's say, try to identify which one will be under equilibrium control and which one will be under kinetic control. So the first or the former example, you know, let's say our time available, let's say, you know, I'm just going to use generic terms here. The time available is much greater than the time or the characteristic time of the reaction. For example, acid-base reactions are remarkably fast, I believe in the order of around milliseconds. So by the time you take your pH reading, let's say, right, which is after 2-3 seconds, the system has had enough time to be able to reach equilibrium now. Yes, so that's a system you would call as equilibrium control. But if I look at the second example now, wherein I have water droplets falling down through the atmosphere under gravity, let's say, and you have carbon dioxide, what do we say, interacting with the outer layer of your water droplet, and here let's say I only have around nanoseconds of times, let's say, right. So here the time available for the reaction, or the time I am looking at, is less than the characteristic time of the reaction, again which is in the order of milliseconds. So what do we say, the milliseconds is the order of your acid base reactions, they are relatively fast. So the second one, where you have relatively less time available for the system to reach its equilibrium, so you are going to say that it's kinetic control now. So why do we need to look at that? Well, because let's say you have come across a system and you need to be able to quantify them, right. You need to be able to know, has the system already reached equilibrium, or is it yet to reach equilibrium, and I need to look at the kinetics now, right. So when it's equilibrium control, do kinetics play any role? Do you care if it's relatively fast or slow? Not really, because when you can identify a particular process as being under equilibrium control, you know that you always have enough time available compared to the characteristic time of the reaction. So you don't really care whether the kinetics is slow or fast. But when we are talking about kinetic control, you know that the system does not have enough time to reach equilibrium, right. And in general you need to look at the kinetics of the system. And then obviously you will always have mixed control when more or less the time available is in the same order of the time of the characteristic time of the reaction. Anyway, let's see, let's look at what we have next, please. And I guess examples, so we already covered that, we are not going to go through that again. Okay, I guess here I wanted to pose a question here. So let's say we are going to look at three cases here. Take a few moments and try to identify which of these would you rather classify as equilibrium control, kinetic control, and mixed control now. So here we have a graph with concentration on the y-axis and time on the x-axis of any particular compound, let's say, and here you have three scenarios, right. Maybe not such a good representation here, so if I can cancel this out and say something like, yeah. So let's say there are three scenarios here, right, that I just represented on the graph. So please take a few moments and think of which one would you classify as equilibrium control, kinetic control, and so on, right. So again here we are talking about looking at the changes in the reaction, the chemical process, pardon me, relevant to the time available. So right, and if you look at this system, you can obviously see that there are no further changes in the system, and you can thus confidently say it's under equilibrium control. And this one, you still see that it's far from reaching equilibrium, and the chemical process is still I guess undergoing, and so this will be kinetic control now. Again, in the former case, which we identified as equilibrium control, we see that the system has had enough time to be able to reach equilibrium, yes, which is not the case with the kinetic control. The system has not had enough time to be able to reach equilibrium, and you still see the concentration changing considerably with time. And obviously the last case is the mixed control, right, when you do see changes initially, but you also see that the system is approaching equilibrium. So in this case, both kinetics and equilibrium play a role here, right. Okay, the next aspect we are going to look at is the relationship between steady state and equilibrium, right. So first, before we go further, while we have already discussed what equilibrium gives us an idea about, we need to discuss what steady state. So people might have heard of it, but there is no harm in looking at it again. And the first question that you need to understand obviously is that steady state is not relevant to only the chemical process now, right, or only to environmental engineering. So steady state is when there is no change in any variable of your system with respect to time. So you look at any variable in the system that you consider, and there should be no change in that variable with respect to time, and that's when you would, let's say, at least I would call the system to be at steady state, right. So let's look at the interplay between some of the steady state and equilibrium, let's say. Some of the examples where we can look at the interplay between steady state and equilibrium, right. For example, now we will consider, I believe, a batch reactor, A batch reactor is one which is a closed system, let's say, and let's say so there are no inputs and outputs, and you have a compound here at concentration C, and that's well mixed, right? And let's say it's decaying, right? So at this particular point in time, is the system at steady state or equilibrium? No, because as we just mentioned, the concentration is still changing with time, right? So neither has it reached equilibrium because the system has not gone to the farthest extent possible, and also neither is it at steady state because the concentration, which is a variable here, is changing with time. So in this zone, neither is it at steady state, neither is it at equilibrium. And if I take the system further and look at it here though, in this particular aspect which, or in this particular time frame which I am highlighting here. So in this particular aspect or at this point in time, the system is at equilibrium because it has gone to the farthest extent possible under the given temperature and pressure conditions, right? And also if you look at it now, there is no change in any other variable too. The concentration is not changing anymore. So you can say that the system has reached both steady state and in equilibrium. So what does that mean? In batch systems, which are closed systems, equilibrium would be equivalent to, let's say, steady state. Again, this is a generic example, so you need to be careful before you apply such generics though, right? So but if it's a continuous flow though, let's say, you know, I have let's say any STP, let's say I have continuous flow coming in and continuous flow going out, and let's say here they are trying to maintain a particular pH now, right? So this is, let's say, we will call that a CSTR, let's say, continuously stirred tank reactor. These are just terms. So continuous flow low. So here, let's say, if I look at it, right, and with time, let's say I plot it, and concentration versus time, and let's say this is what somebody observes as in after 10 days, let's say, starting from 10 days to 20 days, he has taken the sample and he has seen that the concentration or the pH, let's say, on the y-axis is constant. So what conclusions can you draw now? Can you be sure that it's at equilibrium? Can you be sure that it's at steady state? So let's look at this system now. So with respect to steady state, we need to look at is any variable changing with time. So if my only variable is pH, right, and the flow, and I see they are not changing with time, so I can say yes, the system is at steady state. But in this case where we have open flow, you know, how do I know if the system is at equilibrium or not? You know, and this is a case where you need to be relatively vigilant now. So equilibrium is defined only for, or in general, for closed systems, so not for open systems. So what can you do? Let's say you can instantaneously turn off the inlet and outlet, right, and then look at any changes occurring in this particular system. So if I am able to instantaneously turn off the inlet and outlet and see any change in pH, right, then if there is no change, I will say that it's at equilibrium. If there is any change, I will see that, I will say that it's not at equilibrium, right. So again, equilibrium is generally defined for closed systems now, right. So again, there are various examples wherein you can come across, what do we say, a system being at equilibrium and steady state, which we already looked at, system being at equilibrium but not at steady state, system being at steady state and not at equilibrium. You know, there are various examples, but we will go through that during the course of the I guess. So let's move on and see what we have here. So I guess we are going to start talking about equilibrium. So for today, this is the last aspect we are going to talk about, and we'll end with that. So we are going to just discuss introduction. So why is equilibrium important to me, let's say? So for example, in a common effluent treatment plant, I'm concerned with removing the heavy metals, right? So I want to know, let's say, which coagulant or flocculant to use and at what pH should I maintain them. So there are different ways to go about it. You can run the lab test, you can run a full scale or pilot scale test, and then calculate, or try to not calculate, pardon me, measure the changes in the system. But that's time and resource intensive, right? So what can you do though? But if you are able to have the relevant background in this particular course or the chemical process, without doing most of the lab tests, you know, we can more or less relatively accurately, relatively again, because it depends on the other factors which we are always again going to look at, I guess, be able to you know, see or, you know, identify at which pH would we have maximum precipitation of the heavy metals, and then go for the relevant pilot scale or your full scale test rather than spending time and money now. So I want to know what happens to a system when it has gone to the farthest possible extent, right, equilibrium, and that's what I can see here when I'm looking at heavy metal removal at different pH now. Yes. So next aspect and the last aspect which we are going to look at is equilibrium is going to be dependent upon, or is defined by or driven by, not defined by, pardon me, driven by thermodynamics, right? And so we are going to look at what this is about. So equilibrium, I guess, depends upon the delta G or Gibbs free energy or Gibbs energy or Gibbs free energy of the system. That's equal to delta G equal to delta H, change in enthalpy, and T delta S. So change in Gibbs energy or Gibbs free energy of the system, change in enthalpy, change in entropy, and then temperature, right? So as you see, we are defining this Gibbs energy or free energy as a change here, right? So it's a change in one state to the other. So for example, if I say G, right, one state G1 and G2, right, and we are looking at the change in this the Gibbs energy here of the mixtures, let's say, right? And obviously, as you see here, the Gibbs energy is depends upon enthalpy, change in enthalpy. So it changes in the same direction as change in enthalpy, and in the opposite direction as the change in entropy. Entropy will give you an idea about degree of disorder. For example, let's say you have 2 moles. We looked at that particular example with respect to TNT. I think initially we had 2 moles of TNT, and that I believe after combustion there were 8 or 10 moles of gases and solids. So you see that the degree of disorder increased, right? Anyhow, we will come back to that again. So again, Gibbs free energy is defined as the change in what we see is equal to delta H minus T delta S, and delta H is the change in enthalpy, and delta S is the change in entropy, right? And so again, because here we are talking about change, so similar to sea level, let's say we can set any point arbitrarily, but it's not going to be arbitrary. We are going to define it later. We can set any point as your standard or the reference now, right? So that can always be done. So for example, how do you define this G1 or G2? So you define that with respect to your reference here. Yes, so that's one particular case. So I guess I'm out of time, and with that I will stop the class for today, and thank you.